Welcome to the Explainer. So how does a self-driving car actually see the world? I mean, not just dodge a car in front of it, but build a living, breathing map of everything around it, literally in real time? Well, today, we're going to unpack the incredible tech that makes it all happen.
Okay, so here's how we're going to break this down. First, we'll look at the big problem with old-school static maps. Then, we'll dive into the revolution that let cars build their own maps live. After that, we'll see how they give these maps a memory. And finally, we'll get into the race to make this all fast enough to work in a real car.
All right, to really get why live mapping is such a big deal, we got to start with what came before it, the high-definition map, or HD map for short. And this thing is anything but live.
Now you've got to forget about the map on your phone. An HD map is more like a super detailed blueprint for the road itself. It doesn't just show the car where a road is, it tells the car what every little thing is. Every single lane line, every crosswalk, every curb, all of it, down to centimeter-level accuracy.
But making these maps the old way? Wow, it was a monumental task. You had to send out these crazy expensive survey cars to drive and scan every single street. Then came hours and hours of processing. And then, get this, teams of people would manually label every single feature. It was a huge, expensive effort.
And right there, that's the fatal flaw. After all that time, all that money, you have this perfect map that's instantly out of date. The second a construction crew shows up or a city repaints a lane line, your perfect map is now wrong. It's a perfect picture of a world that doesn't exist anymore.
So this huge problem forced a total revolution in thinking. Engineers started asking, what if? Instead of giving the car a perfect but outdated map, what if we could teach the car to make its own map live as it's driving? And that's where the story of online mapping really kicks off.
You know, the first attempts were kind of like an old video game. The car saw the world as a top-down grid of pixels, and it would just color in the squares: road, not road, lane. But a car can't navigate a bunch of colored squares. It needs to see clean, distinct objects, like this specific lane boundary or that crosswalk. It needs a blueprint made of lines and shapes, what we call vectors.
And the researchers really hit the nail on the head. Without being able to tell one lane from another as its own unique object, the map is pretty much useless for the really hard stuff, like planning a complex maneuver. It's the difference between seeing a road and seeing the exact lane I need to be in for my turn.
So what was the big breakthrough? Well, it came from a powerful AI architecture you've probably heard about thanks to things like ChatGPT, the Transformer. Researchers figured out they could use this same tech to build a system that takes in raw camera footage at one end and spits out a fully formed, vectorized map at the other, all in one clean step.
And this chart, wow, it just says it all. You can see the older models on the left, kind of slow, not super accurate, but then the transformer-based models come along and boom, they just blow past everything else in both speed and accuracy. They weren't just a small improvement, they were a total game changer.
Okay, so now the car can create an amazing map in an instant. That's awesome. But what about the next instant? A perfect map that just flickers in and out of existence isn't very helpful, right? The next huge challenge was making the map stable over time.
Just think about it for a second. If your car's building its map based only on what it sees right now, what happens when a big truck drives past and blocks your camera's view of the lane line for a split second? Well, that line would just disappear from the map and then reappear. You'd have this flickering, unstable world that's impossible to drive in.
The solution to this is actually pretty elegant. You give the map a memory. It's a technique called temporal fusion, and it's all about blending the information from the last few seconds with what the car is seeing in the present moment. So, let's go back to our truck example. Before the truck, the car sees the lane line, no problem. As the truck blocks the view, a system with no memory would just see a blank space. But a system with temporal fusion, it remembers the line was there just a second ago, and it can intelligently fill in that gap. The result is a smooth, stable, uninterrupted map, even when things get in the way.
So at this point, we're doing pretty great. The car can build an accurate, stable map, all in real time. But there's one last, absolutely crucial hurdle. Can it do all of this heavy-duty computing on hardware that actually fits in a car and doesn't need its own power plant? This is the efficiency problem.
This led to a huge debate in the field, which basically boiled down to two philosophies. The dense approach is like processing every single pixel of an image. It's super thorough and accurate, but incredibly slow and power-hungry. The sparse approach is smarter. It tries to focus only on the most important points. It's way faster, but historically, it's been less accurate.
And for the longest time, that was just the accepted trade-off. You had to choose, did you want speed or did you want accuracy? It seemed like you couldn't have both. But then a groundbreaking new model came along and just completely changed the game. This model, called SparseMext, was a breakthrough because it was built from the ground up to be smart and efficient. It used a brand new architecture designed just for mapping, a clever training method to get dense-level accuracy, and it even used some basic real-world rules to clean up its own predictions. And the results? They were stunning. It set a new record for accuracy on a key industry benchmark. But here's the truly amazing part. It was more accurate than even the best of the slow, power-hungry, dense models, while being way, way more efficient.
This was a massive moment. It proved that you didn't have to choose between speed and accuracy anymore. You really could have both. It opened up a future where these incredibly powerful perception systems are also efficient enough to actually run in a real car on the road.
And that leaves us with a really fascinating question, not just for cars, but for all of AI. This whole journey, from static maps to dense live maps, and now to these smart, sparse ones, it's really a story about learning what's important. It makes you wonder, is the ultimate form of artificial sight about processing every last pixel? Or is it about having the wisdom to know what truly matters and what you can safely ignore?